Hello and welcome! I'm especially glad about today's video because I finally found some time to come back to my Socket 7 VRM project. Since the last video about this project, quite a lot of time passed, but also it has been going through a couple of iterations. So let me share some exciting news. First of all, it's been a while, so let's briefly recap what happened so far. It started as a small experiment as I got a Socket 5 mainboard with unpopulated voltage regulator module for dual voltage CPUs like Pentium MMX. So I wanted to make a simple module and see if I can get it working. The very first version was sufficient as a prototype and worked well for Pentium MMX CPUs, but was not powerful enough to power AMD K62 CPUs at 400 MHz. The regulator module was able to hold the voltage for a while, but went quickly very hot. So as a prototype that was okay, but after the first step I wanted to dig deeper. Knowledge about CPU voltage regulation is quite useful for the failure analysis, and my understanding in that area was limited, since I am a software engineer and actually have no clue about electronics. And so I dived into the topic, read some literature, talked to some friends who are real electronics engineers, and after a while I ended up with the next iteration of the module. This time it was much more powerful and supported voltages between 1.6 and 3.2 volts. This version was already not bad. It could handle K62 at 400 MHz easily without even getting warm. The voltage was stable and I was quite happy with the result, so much that I considered it good enough to be open sourced. The project can be found on GitHub. This was the state which I presented the last time I made a video about it. And now let's see what happened since that time. As I said, I was happy with this revision, though it was still a prototype with some space for improvements. This version of the modules sometimes didn't start properly when running at 2.2 volts or lower voltage and needed additional reset cycle. Also, with voltages below 3.2 volts, this adapter was not suitable to power single voltage CPUs, which usually need 3.5 volts or more, like AMD K5 or Winchip C6. Another problem was that the DC-DC controller which I used on this version of the module became mostly unavailable or hard to find. So, with all the points in mind, I designed the next iteration, which was based on another DC-DC controller, ISL6545. I improved the layout, added more filter capacitors, and implemented the voltage sense, also called feedback, which takes the connector resistance into account. This is an interesting point. The previous revision, 0.4, just took the voltage feedback directly from the voltage plane on the module, which could be inaccurate since that is not necessarily what actually comes up on the CPU. Intel specs for such a voltage regulator module provide a sense pin which comes from the CPU back into the VRM. This means that the voltage can be better adjusted, taking all the resistance which can appear between the VRM and CPU into account. Not only does it help to provide more exact voltage to the CPU, it also improved the starting behavior of the module significantly, and I had not one issue with that ever since. Since the new DC-DC controller had another reference voltage, I had to recalculate the resistor values for the feedback voltage divider circuit. Those resistors are responsible for the voltage level, which can be set using the dip switches. As I said, I wanted this module to support also single voltage CPUs, which means voltages above 3.2 volts. However, with only 4 dip switches, it was not possible to cover the full range from 1.6 volts to 3.5 volts in 0.1 volts steps. So I shifted the supported voltages a bit. I dropped support for 1.7 volts and 1.9 volts, and therefore could add support for 3.3 volts and 3.5 volts. Adding a bigger range of voltages is not without at all, because the more you spread the range, the more unstable can the voltage get. However, before you write your comments on this, you might want to watch this video to the end first. So this revision 0.5 became more stable, supports a wider range of voltages, and uses parts with better availability. This voltage regulator module in revision 0.5 works beautifully for dual voltage CPUs from Intel Pentium MMX to AMD K6 3 Plus at 400 MHz and 1.8 volts. The voltages are generated absolutely on point. Unfortunately, I have no CPU which would run at 1.6 volts, but at least even that voltage was generated fine. As I said, it is not quite easy to keep voltage stable over a high range of output voltages, but the voltage ripple on this module never exceeds 50 millivolts, usually staying around 25 millivolts. Looks good, right? Not quite. It is definitely an improvement, but is still not perfect for a couple of reasons. During my tests, I realized that I made a mistake, which I will come to a bit later. First, I would like to give you some insights about how I soldered those modules. It uses SMD parts, but I designed it with hand soldering in mind and used bigger 1206 parts. It is okay to build one of those soldering every part by hand, but if you want to solder many at once, it takes quite some time. The module is designed mostly with SMD parts, so I decided to try a heat plate for the first time. For example, one professional space engineering piece of art with super effective ultra-plane surface multi-point automatically adjustable temperature control. But I found it funnier to go with the utter crap, dodgy as hell with adrenaline boost guaranteed during the usage and beyond. Let me introduce to you the utter crap 3000. This thing comes in a bag with a cable attached directly to the heating element glued inside of the plate. It comes with 4 metal standoffs which have to be screwed to the plate. The plate itself is 121 by 70 millimeters and promises to run at 260 degrees Celsius. Mounting the standoffs is easy. The cable has no switch, no manual temperature control, no anything whatsoever. It is as dodgy as it looks. However, to be fair, it does actually what it promises. The plate gets to about 250 to 260 degrees Celsius in around 3 minutes and keeps the temperature quite stable. So I decided to give it a try. As I said, I had no experience in soldering on a heat plate, so please don't laugh about my first steps. As a solder paste, I used this Relife RL403. I have no clue how good or bad it is compared to others, but for me it worked great. I have no stencil to apply the solder paste, so I decided to apply it manually by pressing some solder paste directly on every pad. The first try was terrible. I used too much solder paste, leaving a huge blob on every pad. Then I put every part on top using 2 clunky tweezers. Especially I was not sure about the IC, since the solder paste just ended up as a huge pile of goo with the IC swimming on top. Well, for everything there is a first time, and I knew that I had to practice a little bit. This is a real-time recording and I couldn't stop gazing. First, as the solder paste started to melt and was distributed all over the place, I thought that I messed it up. But then suddenly the paste was pulled back to the pads and magically aligned the parts in places. I had to correct it a bit with my tweezers, but to my astonishment, that did actually work the first try. On my next try, I managed to better control the amount of solder paste which I applied on the pads, so every next module got better and better, but even the first one with crazy amount of solder ended not too bad. I still had to remove tiny bit of solder from the IC pins, but otherwise it was fine. Of course, I tested it for shorts and populated the missing through-hole parts, which still have to be populated by hand. As on the last revision, I again made the coils myself. That is a little bit annoying work if you have to make a couple of those in a row, but after a while I had it done and the new revision was finally ready to be tested. And so we are coming back to the issues which I found with this revision. As I already mentioned, it works great with dual voltage CPUs. The voltage is on point, the ripple is low, the module starts reliably, everything's fine. However, I wanted it to work with single voltage CPUs too, like non-MMX Pentium and AMD K5, Winchip, C6, you name it. Well, the module, as specified by Intel, has 3.3 volts on pins A5, B6 and A6, B6. Left from it there are pins for I/O voltage, and right are pins for the CPU core voltage. Those voltages have to be separated, hence the dual voltage name. The Intel Pentium MMX, as an example for a dual voltage CPU, has inside two voltage planes separated from each other. One for I/O, another one for the core. On this voltage regulator module, the 3.3 volt pins are all hardwired with the I/O pins, delivering 3.3 volts I/O voltage to the CPU. Since in a dual voltage CPU internally I/O voltage is separated from the core voltage, it works fine, and we can set up the desired voltage on the VRM for the core. First, I designed the module with dual voltage CPUs in mind, but then I added higher voltages to the settings to be able to support single voltage CPUs too, which need 3.3 volts or more. However, I didn't think that it is not sufficient. You see, on the module the I/O and the core voltages are separated, which is nice. However, when we connect a single voltage CPU to it, which has only one voltage plane inside, it will connect I/O and core voltages. That means that the 3.3 volts, the I/O and the core pins on the module are all connected through the CPU. The bad thing is that the onboard linear voltage regulator, which supplies 3.3 volts, will take over the whole work because it reacts faster than the switching voltage regulator on the voltage regulator module. A switching voltage regulator always measures the output voltage and decides if it has to turn on or off to keep the level. That's why it has that characteristics voltage ripple. However, if an external linear voltage regulator would keep the voltage already stable at required voltage, the VRM would always remain off, and the whole work would be made by the onboard linear voltage regulator. That means that my changes to extend the voltage settings were useless. This module would be useful for dual voltage CPUs only, and with single voltage CPUs it would just stay off all the time, pushing all the work back to the LDO on the mainboard. Well, it wasn't completely useless. I used the opportunity to play with different voltages, measured the ripple, and experimented with different parts a bit more. Eventually, I was successful and integrated the changes into the new revision 0.6. This time, I separated the I/O pins from the 3.3 volt pins on the module and installed two jumpers which can be used to select between single and dual voltage CPUs. Now, on single voltage CPUs, the I/O pins can be disconnected from the onboard LDO, and on dual voltage CPUs connected as on the previous revision. This simulates a bit the jumpers which are usually preset on mainboards. This way we can forcefully divide the CPU voltage from the onboard LDO from the single voltage CPUs and supply the selected voltage completely by the VRM. As I said, I also used the opportunity to play with the voltages on the last revision, and I decided to extend the switches from 4 to 5. Now the range of the voltages can be set from 1.4 volts through 3.7 volts, which should be sufficient for any socket 5 and socket 7 CPU. The ripple is still okay. The sweet spot is around 2.2 volts, but also with other voltages it usually doesn't go over 50 millivolts and stays within critical limits. Of course, once again I used my dodgy hotplate to solder the new modules, and it saved me a lot of time. After some training with the previous revision, this time I knew exactly how much solder paste to apply to get a clean solder work. I also worked myself through all of the modules by populating the same parts on all modules one at a time. It is a lot faster and easier when you have to open and close bags of tiny SMD parts all the time. As all SMD parts were populated, I just had to put the modules on the heat plate one by one for 2 minutes or so, and after about 10 minutes I got 5 shiny VRM modules. Of course, then followed cleaning with IPA, checking for shorts and soldering the through-hole parts. Again, especially the coils were annoying. I could also design the module with all parts as SMD. That would be nice for automated assembly, but since I still do it manually for power-related parts like coils and capacitors, I decided to use the through-hole parts. However, the distance and the size of the holes for the coil would theoretically allow to use an SMD coil too, though I don't have any at hand which would fit. Anyway, this module in revision 0.6 turned out to be as good that I would say I'm happy with it. I released this revision as usually on GitHub. You can go to releases and download the Gerber files and the parts lists. You can find the information also, of course, on the main page. Please pay attention that the parts have changed from previous revisions, and also switches are now completely differently to set. So if you already have an older revision, pay attention to use the right documentation. And if you don't have any but need one, feel free to build yourself the latest revision 0.6. Of course, there is always space for improvements, but for me it is now good enough and I don't plan to make further changes to this project anytime soon. Now, what is this good for? Well, meanwhile I collected a pile of mainboards with the VRM option. Some I bought, some were donated to my channel. As I showed in the previous videos about it, I already tested it with this Asus mainboard and also Gigabyte. Both modules are based on the Intel 430FX chipset, but I also have some boards based on VIA chipsets, which also support VRM. However, here a connector still has to be soldered. I know that there are Intel 430HX, VX and TX mainboards existing, which also support external VRM, and all those boards can be now upgraded and tested with much more powerful CPUs. Even low voltage K6-3+. I plan to maintain a list of mainboards which were tested with my VRM module. I will update the list as soon as I get my hands on boards which I didn't test yet. However, the most interesting candidates would be OEM machines with custom boards like Compaq, Packard Bell and others from the socket 5 and socket 7 age, which also had VRM option but were usually delivered with low-end single voltage non-MMX Pentium CPUs at 133 MHz or so. Now, those machines could be upgraded to 400 MHz dual voltage CPUs like K6-2 and 3. However, unfortunately, I don't have such PCs at hand, and I would be glad to get some feedback from the community. It would be nice at least to know which PCs would have that option at all. Maybe some of you can even test this VRM and report if it's working for the machine you have. That would be really nice. I, on my end, will test whatever I have here, and I also want to make some benchmarks to compare how different socket 5 chipsets run against each other, utilizing a much more powerful CPU from a Super Socket 7 time. Also how those older VIA and Intel-based boards would keep up against later ALI Aladdin 5 and VIA MVP3 based SuperSocket 7 boards. Those are my plans for a future video, so if you are interested, don't forget to keep an eye on my channel. And for today, this is it. Once again, I'm very happy to present the latest revision of the voltage regulator module to you. You can find the link to the project in the description. Feel free to build it, use it in your retro machines and share your experience. Thank you for watching and goodbye.